Test, test, test. Oh shit. Test, 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 test.
Test, test, test. Okay, it looks like that works probably. Um, all right, that sucks. Yeah, I started up this stream and I just checked it on my phone and the audio was working, and then I started doing the problem, and I guess at some point the audio stopped working. I don't know what that's about. Yeah, just to summarize what I've said, bummer that it didn't record, but I was saying that my initial instinct was to get the subtree sums of each node. So, like, leaf nodes, it would just be the values in those uh, leaf nodes. And then you would recursively backtrack, so it's like 4 and 5 plus 2. So this subtree sum would be 11. 6 and nothings plus 3s. So this subtree sum would be 9, and this whole subtree sum would be 21. So that would be the first half of the solution. And then there would be like an exploration half where once you have those sums, you can then explore the tree again and repeat this process where you are keeping track of it, your answer, which might change, which is the largest product you've seen so far. And on each node, you like cut the left, and you see use this like little algorithm where you if you cut the left, you see what the yourself plus the right would be by subtracting out the left, and if you cut the right, you do the opposite. But in this case, cutting the left would mean we take our sum 21 minus the left tree's sum, which is 11. We get 10. So this is like us plus right equals 10, and then left is 11. We'll multiply them together. That's potentially your new answer. But you keep on going with the left and the right. And then you explore the whole tree that way. And I was just talking about leaf nodes and how you know like when to stop. And I think the first thing is that you don't, for leaf nodes, I think that if it's a complete leaf node, there's no left or right, you just don't do anything because there's no edge to cut. But even if it has one edge, then you, I think, still explore. You do this, except you like you are skipping one of these. You're skipping half of these steps. So if you only have a left, then you're only saying, "What if I cut left?" So yeah, I feel pretty confident. I'm sure that there's probably an edge case I'm missing, but I think I'm going to get started on coding this up. Okay. Oh, and then another thing I said is that I probably wouldn't do this like in production code, but I'm going to use this quirk of Python where you can assign properties to an object, even if they like weren't declared in the initializer. So if we have this like root here, we could say like root.foo equals 42, and that's completely valid. And I'm going to use that to store like this subtree sum property, and that's going to be where for then later for the exploration half. So I'm going to say I'm going to have two helper methods here. I think I'm going to just have like a build subtree sums. This is going to be just, I'll implement this in a sec, and I'm going to have like explore. And this will be the one that does the second half of my solution here. One thing I said that I don't know if it got captured or not is I've never seen a LeetCode problem call out the answer might be too large, so return it modulo 10 to the power 9 plus 7. I don't know if that's a hint, other than like the possibility is Python uses Python like naturally grows its integers into like big numbers. So like this is something I'm going to do for the answer, and I'll make like don't forget to modulo. But I don't think that is something that I would have to worry about in the same way I would have to worry about it if this was C or Java or something like that. Okay, so I'm going to work on this build subtree sums. So the first thing is like if node is none, that means like we went past the edge of a node or a leaf node, then you don't have to do anything. So I'm going to say left sum equals self dot build subtree sums no dot left. Oh, I guess this is I guess it would be easier if this returns the sums. And you know that works. R sum equals self dot build subtree sums no dot right. Self sum equals L sum plus R sum plus no dot value or val. And then, like I said, I'm gonna introduce this oddity, store it there, but I'm also then gonna have to return it. Cool. Okay, so I think that should be enough to get all the subtree sums. So just running through that, we start here at 1. It's not none, but we're going to recursively call here to 2. It's not none, but we're going to recursively call here to 4. It's not none, so we're going to recursively call to the left. You could probably like optimize check left and right are defined so that you save some function calls on the leaf nodes. But we call 4 left, and that is none, so we return 0. We call 4 right, and that is also none, so we return 0. So this should be 0, and this should be 0. And now the self sum is 0 plus 0 plus no dot val, which is 4. So we return up 4 here. Now here, this is 4. We go down to the 5. I think I can skip ahead. It should be 5. The and one thing is we're also setting this extra value. Then this is 4 plus 5 plus 2, so that's 11. Returns up to here. The right is, we'll have, this will be 6, 9, 9, 11 plus 9 plus 1 is 21. So I think that works. So I'm just going to start by saying, like, I don't think I need this value, but self dot build subtree sums of the root. Okay, so now I need to, I'll say like answer equals self dot explore of the root as well. So now for this part, whoops. Sure. Sorry, oh, it does work. Okay. I didn't think that shortcut would work. Okay, so let's see. There are a few ways that, so keep track of the largest product. There are like a few ways one could do this. Like this could either be the return value of the function, which I mean, I have it set up to be the return value of this helper function, so maybe I should just roll with that. But one thing that's sometimes easy to do is to just be passing around like a reference to a number, which if you just like pass in like answer of int, that won't work. It's like sometimes easier to just like wrap it in a class and then be passing around the reference to a class. But I'm going to try to roll with this, where what we're doing is we're returning the answer. Although now that I say that, well, can I do something similar? I guess like the interesting thing is like if you just break this problem down into the recursive case, it's like the answer of this larger tree is like the maximum possible answer of, you know, like itself and the two subtrees. So like if we look at this 4, 2, 5 case, just focusing like let's pretend 2 was our root here. What would be the answer? So if we cut 4, then it would be 4 times 7, which is 28. We cut 5, it would be 5 times 30. So the answer would be like 30. So like the answer of this subtree is 30. The answer of this tree, I guess, is 18 because there's only one thing to cut. And then it's like the sum of this whole thing is, or the answer of this whole thing is 21. But I'm not sure it really makes sense to keep track of these answers because you can't, like the subproblem doesn't have any impact, I don't think. Like you wouldn't pick 18 or 21, I don't think, because you need to use all the nodes. So scratch that. I'm not gonna, it doesn't matter. I think that I'm gonna go with like a little bit of a what I was describing before, which is just like pass around a reference. I'm using Python data classes here, which if you're like familiar with, like, I'd say a kind of closest analogy is like Scala case classes or something like that. But let's see. It doesn't say anything that they're integers, so I guess they should. I guess that's actually a good thing to call out, that that they are not integers, and this doesn't have to be an integer either, and neither does this. And this is actually going to, I'm going to change the types around here. So I'm just going to say at the start we don't have an answer. Is there any case where the number of nodes in the tree is guaranteed to be start at 2? So we always have a cut. So like after we do our exploring, we'll always have an answer. It's like not possible. This is the sort of thing where like I maybe would check this in production code, but instead I'm just going to say assert ans.val is not none. Basically that we got a value, and then like I said, don't forget to module. Okay, so yeah, let's get started. And this is now just doing side effects of possibly updating the answer. So I think I'm ready to code this part up. So we're at this node. I think the first thing is that actually, it's interesting that this is passed as an optional tree node, because they say, you know, there's the root there's at least 2 nodes, so there has to be a root, but that might just be a LeetCode thing. Cool. So I don't have to do the same thing where I'm checking for the node is none. I just have to do these first two steps, which is like, what if I cut left? So, like I said, it's like, oh, well, so I guess, can I cut left is like the first question, which is like, if node dot left, and this will only be true if node dot left is not none. So what would it be? It would be left subtree sum equals node dot left dot subtree sum, and then me plus right, is a goofy name, equals node dot subtree sum minus left subtree sum. It's also interesting that they're all the values are between 1. They're all positive. No zeros, no negatives. So now left cut product equals left subtree so I calculated this value, the 121 value here, and then I'm basically just storing here, like, is it the answer? And it's like not really, like, it's important that we potentially update this value if it is the answer, but it's not important, like, there's no other branching. So then it's like, can I cut right? If node dot right subtree sum equals node dot right dot subtree sum me plus left equals node dot subtree sum minus right subtree sum right cut product equals okay. So the answers are 2 checks, but now we need to potentially repeat with the left and repeat with the right. And we can only repeat with the left and right if they exist. So again, it's similarly like if node dot left, we want to call this recursive function with node dot left. Pass in the reference to our answer. If node dot right, and then the return in Python's implicit. Okay, so then we should have our answer here, and then we need to modulo this value. So I think it's just return ans.val modulo. I can't remember if power is like a built-in, if I need to import it from math or not. Let me take a quick look. Yes, okay. How can 9 plus 7? I'll keep that comment even though. Okay, let's take a quick look at this part. So the explore part. So we've already talked a fair amount through the first like root.left example. It's our answer, but like let's check out root.right. I guess I should take a look. Like, I'm pretty sure that this code would check out. If it doesn't, I'll find out really quickly in the example. But node.right so the subtree here is 9. Me plus left is 21 minus 9, which is 12. Right cut product equals 9 times 12, which is 96, and the answer wouldn't be updated here because this is already 121. This is 96. This stays 121. Then we do have a left. Oh. Yeah, I think so. Yeah, okay, yeah. We have a left here. We're going to repeat this process here. And we're like, do we cut 4? Well, if we cut 4, then it's 4 times 4. Oh, this doesn't work, right? Because this subtree's, it's not just for this cut here with the 4. Now the two trees are 4 and everything else. It's not just 4 and 2 and 5. Yeah, so that's interesting. Like, is the answer that we need to add the parent? Like, if there is a parent? Let's take a look at this example. Because yeah, I think so. Because if we didn't add the parent, then this would be 5, and we would incorrectly say that this sum is 5 times 15, which I think is 75. Okay, yeah. So that's a problem. So yeah, I guess you do need like a parent. And like a parent sum. You could either pass in a reference to the parent, or we could just pass in like parent sum. Parent sum there, the me plus right equals sum. Is that right? What is the parent sum for the root? Because here, here it it's like the parent sum including itself but not you. Oh, that's so complicated. I feel like there's an easier way to express this. Because yeah, it's complicated because this for the root this is 0, and obviously it's not 0 minus 11. It's and here we do need to take into account that it's not just one is like the rest of the tree. Oh god, so maybe there's probably an easier way, like a more concise way to do this, but it's like, is there a way to like, it's like the sum of the subtree except this cut. It's like the root, like in this example here, what's the whole tree sum? It's 11, 15, 18, 20, 21. Oh, they're both 21. Oh, it's the same numbers. It's just rearranged. So when we uh, oh, I guess it's like you can just pass in. It's like the whole root of the tree, or like the whole sum of the tree, is the other half. So it's like tree sum, right? Because you're always cutting it into half. You're either cutting it into like, it's either like the new subtree and the other half. You're cutting it into two parts, not necessarily half. So it's actually like just the tree sum is the what you're doing here. And let's tree sum. And the tree sum for the root is the root dot subtree sum. Is that the right? So okay, let's reevaluate this new answer. And I also need to update these other call sites. But luckily it's just the tree sum. It's a constant for that answer once we come up with the tree sum. So yeah, so whenever we call explore, we're going to, in both of these examples, the tree sum equals 21. And we're just basically saying, like, if we removed the left subtree sum from the tree sum, the total tree sum, and the right, and then also the right, what's the product of that? I think that works. Let's take a look at this example. So here again, the subtree sum is 21. When we get to here, the this is 15 is this subtree sum. So it is correctly that it's like this right is 15. 21 minus 15 is 6. So I think that works. It's just that we need to know, like, we're cutting it into two parts. What's the second part? Two halves. Or not halves. Two parts. Okay. I'm sure that I have some errors somewhere, but yep. Line 45. $80. Oh, right. Okay. So this is like saying this is none originally, so like if not is, or if is dot val is none, is dot val equals left cut product, and we need to do that in two places. We need to do this logic in two places. And this, you know, you could maybe do like, I don't know, the maximum. I don't know if Python has like a way to do like maximum negative value so that you could just initialize this value. Like it doesn't have to be potentially none. You just like initialize it to maximum negative value, but this works fine. Just something we have to remember. That's because it's a spelling typo. You don't pass self. What am I doing? Oh, well, it's weird that it wants a integer, but it seems like it could be numbers. I mean, I guess it does say, no, it doesn't say that it's an integer anywhere. Well, I'm just going to cast it to an int. And hope that works. Okay. Nice. Okay. So to summarize, the key insight is that like you're cutting the tree in half, so you need to know the tree's whole sum, And then you're like just figuring out, okay, what am I removing from that half? And then you're just like doing the products. That part is easy. And then the time complexity is O of n. The memory complexity is also linear. You need extra memory to store the subtrees, the subtree sums, and also like recursion stack frames, whatnot. Okay, peace.